All right, so here we go. Lecture 23. All right, so now what we need to prove is that this one here, f dr throughout the contour will be equal to because f from the previous page, we know that f, if it's conservative, is equal, you can write it under the function of the potential, no? All right, so the proof is very simple, really. What does that mean? This will be equal to minus the integral of the contour through what? Through what? What is the definition of this? Will be partial of phi partial x dx plus partial of phi partial y dy plus partial of phi partial of z dz. Okay? And let me do a figure over here if you want of what you're trying to do. This is C now. Let's say we have a point A here and B. So really it should just be equal to minus the integral of the full derivative, no, of the function. This is the same. And now, I mean, since this is around the contour and it's close, so basically, let's say you integrate between A and B, you go here. But if you integrate around the whole contour, you go to A and you end up at B, no? So what should be that integral equal to? If you start at one point, you end up to the same point, is 0, no? Okay, so really this will mean that f dr and the contour, this is an f, is equal to minus this here d theta will be equal to 0. And basically the reason is it is 0 because the loop or the curve, or if you want the curve, is closed, no? If it was an open boundary, it will be a different story, no? Okay? So you want, basically, you start from one point and you end up at the same point. That's the only thing that matters. Okay, so I know I mentioned the examples to you in class, but since we have time, let's just put here the examples. Very quick. Okay, let's start maybe by the first one. That will be the gravitational force or gravitational potential energy, okay? It should be eccentric. So if the gravitational force is a conservative force, you should be able to write it under the form of a potential, okay? So basically, if we look at what is the work done by the gravitational force? So the expression, I will do a figure now, will be what? Minus mg, I do a figure now. Let me do the figure. Maybe that's what I should have done first. Y, X. So this is your body with the CG. You agree that every time you do this sketch, you have the force is mg going down. And if y is going up, there should be minus mg, no? Now, dr in this case is only on the y direction. So it should be dy. So this should give you minus mg. And let's say you have 2 points, y of b minus y of a. And this is generally defined as whatever, h. No, you are familiar with h. So basically that tells you that the work done by the gravitational force, which is F dr, is equal to minus mgh, okay? And this should be work. So you see, and this is really what you call potential energy, no? But you really see that the definition is that it's work done by a force, by the gravitational force. So let's call this one I. Okay, so we could say that if F is conservative, then you should be able to rewrite it as F equal to minus the del of a potential function. Okay, and if you want, using this over here, since we did this derivation here, I could do it differently, but let's do that one. So using the information above, what do we have? We have the integral of f dr. So I'm using this expression here, should be equal to what? Minus the integral of the phi, which should be here equal to phi of a minus or phi of b. Sorry, I put yb. Well, this is a minus sign, so should be minus phi of b minus phi of a. That way I don't have to scratch phi of b. Okay, I mean, we could do it differently, but we're probably going to do it the other way as well for validation. So now, if we compare these two expressions, here you know phi is a potential function. So if you compare Latin 1 and 2, I mean, this is very simple. It's so simple that I had time to, to write it, okay? Basically, if you compare these two, what can you say? That the potential function is equal basically to minus mgh, or that would be negative mgy, no? Okay. So that now if we go and check, so if this is the potential function, that means that f is equal to the negative of the potential function, which in 1D will be partial of y of negative mgy, which will tell you that the expression for the gravitational force is mg, which is true, no? Yeah, I mean, it's so simple, but this is basically what the definition of gravitational force is. And we're going to do now The other one, I'm not going to do it I'm going to do it very simple. The one of the spring, we already talked about it like 3 times. Okay, and the second example will be, oops, this should be on my notes. Okay, and the other example, let's say, would be spring force. Okay, let me just do the figure first here. Let's say we have a spring. If you apply the force over here, is equal to kx, no? The force of the spring. So basically, if we look at the work done by the spring force, V should be equal to what? Integral of minus kx, and for 1d, dr will be dx. So this will be negative 1/2 kx squared. So again, comparing as before, we could assume that then the potential function here will be minus 1/2 kx squared. Okay? So if this is true, so if f is conservative, what do we know? The force should be equal to the negative of the gradient of the potential function. And this would just give minus partial x of minus 1/2 kx squared. We should give you what? The expression for the value of the force, that is kx, no? Which is the force of the spring. Okay, now I'm going to cover something that I've never covered in this class, but I think might be important. I think I mentioned to you the other day, what would be the Lagrange equations, okay? Because this is also part of the potential theory, if you want, okay? Would be an application. So let me put over here Lagrange equation. Okay, so over here, I'm just trying to combine a bit everything. All right, so what is Newton's law? What is Newton's second law? Is summation of forces equal to ma. All right, now what happens if the forces are conservative? If the forces are conservative, we know we can rewrite it under the function of a potential function. That's what they call that, potential energy. Okay, and this is, if you want, conservative force Okay, so let's say combining the above two equations, I'm going to do this. Last time I dropped all my notes behind the stuff. I'll call IT. So combining the two equations, what are we going to get? We're going to get summation of forces equals to MA. If I simplify, I could say this will be minus this equal to MA. Okay? Or I can just write this as minus this will be equal to what? I hope you all know this. So I'm just going to do a derivation in 1D for simplicity. So if you want a derivation in 1D for simplicity. Okay, basically of the notation. Even though we can try to do it, it should not be that bad. Let's do this. It would be dx. I could put some index, no, I. That way would be the 3, but I just do 1. So it should be what? Second derivative of x with respect to the time, no? Or is dv/dt or the second derivative? All right. So let me just rewrite this a little bit differently. So this should be equal to minus. This will be equal to m d dt, and I'm going to do the proof now. Of 1/2 d, be careful here, dx dot of x dot square. I mean, you can see now basically what's happening. What is really this term? I left the m outside, but m is a constant. I could put it outside, no? So it should be 1/2 mv squared, no? Okay. But let's check this part over here. All right. So you want, I'm going to prove this part. So let's say here, check. So d dt 1/2 d dx dot of x dot square. This is equal to what? D dt. What's going to happen inside the bracket? This is going to be 1/2 of dx dot. So it should be now 2 x dot. Yeah. And if you want, you can put here dx dot. I mean, we don't have to put it, but let me just put it. Might be more clear for you. Dx dot over dx dot. You don't have to put it. You know it's 1, no? Johnny, when you do, what is the derivative of x squared? You say it's 2x. You don't say it's 2x dx, no? But basically it's the same thing. And now, basically this will give you what? This 1/2 disappears. This one obviously is 1. And now if you take the derivative of this one, of x dot with respect to t, this will give you x double dot, which is this term over here, no? Yeah. So basically you can write this under this form. So bad thing, I need to go to the next page. So let's see here, therefore, We have what? Minus, let me just write this, would be equal, I write the last page, would be equal to d dt of 1/2. Now be careful because m was constant. I can put it anywhere I want, no? X dot square. And if you want to put it over here, you should all be aware that x dot is the same thing as the velocity. Or if you want, let's write it under that form. We have minus the potential function equal to d dt of 1/2 mv squared. And yes, this is what is known as the kinetic energy. So kinetic energy exists. Potential energy is a name, no? And let's say this will be our K. So this will mean at the end that we have minus the one of the potential function will be equal to d, oops, what did I do here? I forgot. Oh guys, I forgot something. I forgot to write something because when I went from here to here, I forgot to put the d over dx dot. So sorry for that. Let me just rewrite this very quick. It's gonna be faster than to scratch everything. So you can make the corrections, but so it is clear on the notes. So let's see, I can write here, therefore, we have that minus phi will be equal to d dt of 1/2 d, this is the term that I forgot, d dx dot of m x dot square. We say that x dot equal dx dt, same thing as the velocity. So this will give us that the negative of the gradient equal d dt of, let's not forget this term, d dx dot of 1/2 m v square, where this term over here is the kinetic energy. And we're going to use the letter K, capital K. So from here we can write that minus that of the potential function will be equal to d dt of dk dx dot. Okay? Or this is the simplified, this is really the simplified Lagrangian. If you want, then I'll give you the full. Or we can just say this would be equal to d dt dk dx dot plus the gradient of the potential function equal to 0. Okay? So if you want, this will be my version of the simplified Lagrange equation. Okay, so the important part to understand is that this equation, so this equation is equivalent to which equation? Summation of forces equals to MA, no? For conservative forces, okay? Is equivalent to summation of forces equal to MA for conservative forces. So basically, they should give you the same thing, the same results. Otherwise, we'll be in trouble. Okay, so let's try to do a quick example, and then at the end, I'll give you the expanded version of the Lagrange equation. So let's say here, example. I'm going to do a very simple example. So this is generally used, I mean, it can be used for many, many things. But at least in vibration is used to say, derive the equation of motion for the below system, okay? So, and let's say our below system is just a mass attached to a spring. So this will be K, and this will be M. All right, simple, no? And what did we just study? Potential energy, mgh, spring force 1/2 kx squared, no? So it should kind of work. All right, so procedure, back to statics, dynamics. First thing you need to do is what? Free body diagram. Always the same thing. Really, it's not a free body diagram because this will be moving. You can call it like dynamic free body diagram, but let's say you do first a figure, which should be what? So if you do, so here what I'm writing is summation of forces equals to MA. So personally, I like to do one diagram for the left-hand side, one for the right-hand side, one for the forces, one for the inertia effects. So if we go from this figure to this figure, what are we going to have acting over here? Down, we're going to have acting gravity, mg, and this is not going to fall because the spring is going to be creating a force, kx, no? But now, this, if we assume you pull down, this will be moving down with MA, or which will be mx double dot. So we need to specify some type of reference frame. Here, probably the easiest to specify that one as being positive. Okay, I mean, you can do it differently, but it's fine. Okay, so now this is generally the first thing you do, the figure or free body diagram. Then from the figure, you write down the equation. Okay, so if you write down the equation, is positive is down, this will give you what? Positive mg minus kx will be equal to m x double dot. So finally, the equation of motion of this will just be m x double dot plus kx equal to mg. I'm going to leave it here. You can remove this mg You can remove it, okay? But this is not, I'm not going to do it. But basically, you recognize this as being the equation of motion, okay? For the spring damper system. So equation of motion for the problem. So it's all different notation without my notes, but it should work. So now, next, let us use the Lagrange equation that we say is equal to what? D dt of dk dx dot plus del of the potential function equal to 0. So in this system over here, maybe I can redo the figure here very quick. For this system over here, what would be the kinetic energy? What would be the kinetic energy? There is not two kinetic energies, only one. It's 1/2 mv squared. That will be 1/2 m x dot squared. Okay, and in this case, I know I don't like to call it that way, but we say phi should be, let's say, let's call it our potential. You know, I don't like it to call it that way, but let's say it's potential function, potential energy. That's what they call it, energy. What are we going to have? So we're going to have 1/2 kx squared, correct? Minus, what was the one of the potential field? mg h, but in this case, the h will be x, correct? All right, so. Okay, so let's substitute into this equation. So let's look first at the first term. So then d dt, let's do one term at a time. And we can maybe do both of them. Yeah, I think we can do both of them. This will be equal to what? D dx dot of 1/2 m x dot square plus for 1d, this should be equal to what? What would that be? D dx, no? Of 1/2 k squared minus mgx equal to 0. So magically, I mean, not magically, but you say that this will be equal to what? I mean, let's do in 2 lines, d dt. What are you going to get over here? That was just like the derivation. You're going to get m x dot, because the 2 will cancel, plus kx minus mg. So at the end, or before, you see this will be equal to what? M x double dot plus kx minus mg equal to 0, or mx dot plus kx equal to mg as expected, no? So you see that generally people, I mean, the Lagrange equation is one of those things that makes very difficult problems easier, but make easy problems a lot more difficult. So, you know, it's like, it's one of those tools, you know, it's like, it's a good power tool for complicated problems, but it's not a good power tool for simple problems. All right, but a lot of stuff comes from that. I mean, really a lot, okay, of applications you can find. All right, so if you want, let me give you, and that will be the last thing I wrote on the notes. So 136, 137. All right, so the real, I mean, and this even more than this one, but let me see how can I help. All right, so this right over here. All right, so let's see over here will be, instead of the simplified, let's say expanded Lagrange equation, because this is the way generally you will find it, and even more complicated. So basically we had before, so recalling, that we had this part over here will be equal to d dt of the, oops, I forgot again the other ddx. So I'm not gonna write the page this time, minus this is equal to d dt of d dx dot of k. Okay, so now maybe you see it because of the case we did, but generally what they do is this: add in one term on each side whose derivative is 0. Basically, on the example we did before, you saw here that the value for the potential energy was 0, and when we did the other term, whatever it was for the kinetic energy was 0. Okay, so basically what we do over here is we're gonna have minus this of, let me now change this stuff. You change the sign here, or? Okay, so we do here k minus phi will be equal to d dt d dx dot of k minus phi. Basically, it's the same now, just a constant. Or this is just defined as minus del of L equal d dt of d of L dx dot, where you can imagine that this L is k minus phi, is known as the Lagrangian. So if you want, this will be the classic Lagrange equation. But I think the other is going to give you the same results, and it's a little bit easier, no? So if you did, you're probably not going to remember, but if you did structures 2 aerospace, you had all those things about the principle of minimum potential energy to find the deformations. You probably don't remember, but all based on this, okay? And this will be it of the class notes. I'm not going to add anything else.